We started talking about really the first chapter, which in our class here, which is kinetics. Remember that kinetics deals with how fast or slow a reaction takes place. So when we're talking about kinetics, it does deal with really how sort of fast or slow a reaction takes place, or really the reaction speed. We talked about a couple of things. First off, we talked about really what is sometimes referred to as the rate expression. And the rate expression, when you do have any type of sort of reaction such as this, you can write a rate expression where the rate is equal to minus 1 over A, the change in the concentration of A, over the change in time, equals minus 1 over B, change in concentration of B over time. And this would be 1 over C, change in concentration of C over time. Couple of things that we talked about, our reactants should be decreasing with time. So as we did some examples, we do want to include the negative here because when you do calculate the average rate for the reaction, it should be a positive number. And the reactants, because they are decreasing with time, their final concentration will be less than their initial concentration. So when you do the change in concentration part, you'll get a negative number, and that negative will turn the reaction rate into a positive number. Now, the products are a little bit different. They should be increasing with time, as we talked about. So what we see there is actually our final product concentration should be larger than our initial concentration. So that, again, does give us a positive number when we do the change in the concentration, and again, giving us a positive rate. The benefits of the rate expression is if you know basically one piece of information about the reaction, if you know perhaps the average rate, or you know the rate at which a reactant is changing with time, or a rate at which a product is changing with time, you basically can figure out how on average everybody is changing that reaction over a period of time. So remember, we get something like 0.008 molar per second. Again, on average, you know, if that was the average rate, everybody's averagely changing about that much concentration per unit of time. We also talked a little bit about the idea of instantaneous rate versus average rate. Again, much like the driving example I think I used, although on your average trip, you may have drove a specific sort of miles per hour, there might be periods along the way that you maybe were traveling faster or slower. And same thing with reactions. There could be periods, obviously, along the way where a particular reaction or product may be changing a little bit faster, but on an average, we sort of look at it. Now, when we talk about rate expression, we also take 1 over the coefficient, and we do need to take into account the stoichiometry, or the mole to mole relationship between the reactants, products, or whatever we may be looking at. So by taking 1 over the coefficient, as we did in several examples, that sort of combines both the stoichiometry part of the calculation and also the kinetics part of the calculation kind of together in one sort of move. I think on the very last example, we saw that if you wanted to, you could kind of do it like a stoichiometry problem first, and then kind of do the kinetics part of it and the rates part of it sort of second, and it works out both ways. But if you kind of want to kind of do them all together, you can take 1 over the coefficient, and that will do it for you. We also then started talking about the rate law. And the rate law is a little bit different than the rate expression. It has usually a formula of something like this, for example. Where this is the rate constant, which for the most part, you know, if it's a large value, it will mean that the reaction will occur pretty quickly. If it's sort of a smaller value, then it'll be kind of a slower rate for that reaction. The X and Y in this case are, as we talked about last time, what are referred to as orders. And they're actually found experimentally, which is what we're going to talk about next, how to actually find them. But the benefits of sort of knowing the orders for each of the reactants and sort of knowing the rate laws we talked about at the very, very end of last time is the idea of, you know, if you are doing a particular reaction, for example, and maybe it's happening too quickly for you, we might have that next week when we do some experiments. You may want to figure out maybe how to slow up that reaction, or you may want to actually speed up a reaction if it's sort of occurring a little bit too slow. So the orders are sort of, again, the proportions of each of those reactants that you need to kind of toss in there to basically maintain a specific rate of a reaction to take place. Now, depending really on the orders of those reactants, some may have a much greater effect on the rate of a reaction than others. So for example, we talked about the very end there that if you had something to the 0 order, right, that basically equals 1, which means, frankly, you could change as much of that guy's concentration as you want. It really will probably have no factor on the overall rate of the reaction. As opposed to if you had, say, a reactant was, say, 2nd order, where even by simply doubling, for example, that concentration, it could have a much greater effect than if you maybe took a reactant that had a 1st order and sort of doubled it. It would obviously increase the rate, but not to the extent of obviously playing with the other. So those are, again, sort of the practical applications of knowing the rate law, knowing the orders. It really does allow you to sort of, modify the reaction, figure out, what's really the important reactants or reactants that affect the overall rate. The other important thing is a couple of things. First off, there's absolutely usually no products in a rate law. So the rate law is all about reactants only, no products being found. And like I said, although X and Y are the orders, they are not the coefficients in the balance equation. They may end up being the same number, but that, again, is not how you get those guys. You do have to find them experimentally, which means you do have to do some type of calculation usually to sort of figure that out. Any question on anything we talked about there last time? All right, so let's actually then talk about, how we can actually find the orders of these reactions. And typically speaking, the way that we can find the orders of reactions is you will typically be given, like we just saw there, really a table in most cases. And in that table, you'll have some information given to you. You will typically have a table that has a concentration of reactants present, and it'll also have the initial rates for those guys for different experiments. For example, 1, 2, 3, say this was 4, and we'll do 4, and this was like 10. And this guy we'll say is 2, and this guy is 4, and we'll go with 15. And we'll just say, hey, this is 4. And that's 4. Actually, that's bad example there for 4. Let's go with actually 2 on this one. 2 and 6 here. We'll do that. And then actually we'll do 2, 2, not 6. Let's do 8. And we'll just have a rate of 30, for example. So these are some typical sort of numbers, obviously not whole numbers you usually won't get, but you'll have a table that looks something like this. And what we're looking at is really the effect of changing the concentrations and the actual rate that occurs as you change this concentration. So we could use a table like this to figure out the orders of each reactant and ultimately the actual rate law. And then we could figure out really the value of the rate constant at that point. So if we were to just write a generic rate law for this, this would be the rate is equal to K times A to the X and B to the Y. So the purpose here is you can look at it and sort of figure out how things are changing if you understand how concentrations are changing and rates are changing. But for most people, a mathematical approach is usually probably a safer sort of bet to do. So we oftentimes will use sort of this formula here when we're trying to figure out the orders and stuff like that. And that is rate 2 divided by rate 1 is equal to K times A to the X and B to the Y. And this would be K A to the X and B to the Y. So when we say rate 1 and rate 2, it does not mean that you go to this table and select the first and second entry. That's really not what it means. What it means is we want to go to the table basically and select 2 entries. Now, it's important when we select these entries that we actually find 2 entries where one of the reactants remains constant in terms of their concentration and the other one basically varies. So if I were to go to this table, I could choose experiment 1 and experiment 2. in that experiment, my B stays constant, but my concentration there sort of varies as well. And I don't like my choices here. When we redo these, I can go with 20 and we'll go 10 here. So when we go to choose these, specifically speaking, a lot of times you might want to put the larger rate up on top. You don't always have to do that, but it oftentimes will give you sort of a whole number, a little bit more whole numbers. You could do it the other way around, but sometimes you'll get decimals and stuff like that. So for example, if I were to do this, I would go into here and I would take 20 is equal to K times 4 to the X and 4 to the Y in this case. And that's all the information from the first entry in the table. I then would go back and put all the entry for the second guy into the table. And that would obviously be all the entries there. Now, the reason why we want to choose one or two entries where one of them stays constant is we really don't want too many unknowns, right? It makes it a little bit hard to solve. So we really just want one unknown. So let's see here. I played with the numbers. Let's see how bad I did. So if we do this, right, and we divide this, this is going to give us 2, I believe, right? And this is the rate constant here, and this is the rate constant here, which means at this point, we really don't know what it is, but it is the rate constant. So should those numbers be different or should they be the same? It should be the same, right? So although we don't know what it is at this point, it should cancel out those two numbers. When I take 4 to the X divided by 2 to the X, that leaves me 2 to the X when those guys cancel. Once again, here, we don't know what Y is at this moment, but we do know that it should be the same because it's the same reaction, which means that these guys should also completely cancel out. That now gives me 2 is equal to 2 to the X, which is a common sort of guy that you get here. We could solve for X, and X in this case would equal 1. And that is how you can sort of use the table to figure out the order, right? By the way, if it didn't have really pretty numbers like this, you could take the natural log of both sides. When you do that, the X will come down, and then you can divide the natural log of both sides. You get 1. So in case you don't get really pretty numbers, which does happen, that's basically how you do it. You can take the natural log of both sides, then divide obviously it to the other side, and that will get you your number on the end. So that would then tell us what the order is with respect to A. We would then want to go back to our table, and we would then want to pick 2 entries where we keep actually A constant, but vary B. And in this case here, it would be experiment 2. That was not what I was looking for there. And experiment 3 that would do that. And we basically would do the exact same thing and get the order for B in this case. I won't do it because I just made up the numbers, so I'm not confident how great it's going to turn out. But that's what you would do. At that point, you will now experimentally determine the orders for each of the reactants. And you would have actually what the value of this guy is and what the value of this guy is. That then would allow you to actually use the rate law to go back and actually solve for what the value of K would be. So I would highly recommend this sort of mathematical approach to this. You can, like I said, look at it and go, well, I doubled the concentration, I doubled the rate, so it's like a 1-to-1 sort of relationship, or I doubled it and it went up by 4, so maybe it's a 1-to-2 relationship. So you can kind of do that, but the mathematical approach is probably the better way. So why don't we try one here together, again, looking at some real numbers here instead of ones I made up. So we have this reaction here, which is F2 plus 2ClO2 goes to FClO2. And again, in kinetics, you get a lot of tables, and this is again a very common table. So we have some initial we have some concentrations of F2 and ClO2. We also have the initial rates of each of those. So in this particular case, what I would want to do is look at my table here, and I would want to find again 2 entries where we keep one of the concentrations the same and vary the other. And very easily, I could see that obviously here, the first and the second one will keep the F2 concentration basically constant, and it will vary obviously the other one. So that's what I'm going to focus in on here first. I'm going to look at experiments 1 and 2. If I were to start with just the generic rate law, it would be the rate is equal to K times the concentration of F2 to the X and ClO2 to the Y in this case. So looking at experiments 1 and 2, we're just going to put those information in. Once again, I'm going to select the one that has the larger rate and put that up on top so I can maybe hit some kind of whole numbers as I go through it. So in this case, I would have 4.8 times 10 to the minus 3, it looks like, molar seconds, is equal to K times the concentration there in number 2 for our F2, which is 0.1 to the X. And the concentration here for our second guy, which is 0.04 molar to the Y. So everything I just put there all comes from entry number 2 in the table. I'm now going to do the exact same thing for entry number 1 on the bottom. So that would give me a 1.2 times 10 to the minus 3 molar seconds is equal to K times R 0.1 molar and R 0.01 molar to the Y. Again, these should be molar up here. All right, now we could use a math. So if I do a little division here, that should give me a 4. Once again, the rate constants should completely cancel. These guys here, which are the same concentrations, should also completely cancel. Now, when I do the division here at the end, that is going to give me a 4 to the Y. Once again, you could probably just visually see that Y in this case is going to equal 1. So that would be the order for ClO2 based on the experimental data that we got going on. Any questions on that calculation? Now, once we figured out that guy, what we might want to do here is come back and we're going to keep the ClO2 constant and we want to vary the F2. So it looks like from the table to do that, we could keep the guy constant by doing number 1 and number 3 from the table. We'll keep those guys constant. And again, that would also vary the F2 concentration. So looking at 1 and 3 in this case, once again, I'm going to put the larger rate up on top. So for that, that is number 3. So that will give me 2.4 times 10 to the minus 3. It's equal to K times 0.2 to the X, 0.01 to the Y. And now we're going to put all the information for number 1 on the bottom, which would be 1.2 times 10 to the minus 3. Our K, 0.1 to the X, 0.01 to the Y. Once again, here we're going to do a little bit of math. So in this case, we've got some nice numbers working. So this is going to be a 2. This is going to cancel. This will give us a 2 to the X. And once again, this will actually completely cancel out. So in this case, X would equal 1. So the order with respect to F2 is going to be first order as well. Now that we actually have the orders for each of these found experimentally, we could write the correct rate law here, which the rate would equal K times F2 times ClO2. Much like anything else in chemistry, if it is 1, we don't need to put it up on top. So it's assumed obviously to be first order. The overall order in this case would be what? It would be second order. F2 is first order. ClO2 is first order. Gives you a second order reaction overall. Any questions on that so far? At this point, once we have successfully found the actual orders for each of these guys, we now can use our completed rate law to figure out what is the value of the rate constant. So if we take our rate law, which was the rate is equal to K times F2 times ClO2, and we solve for K, K would equal the rate divided by F2 and ClO2, right? So where can I get all these numbers? Where I could get these numbers are actually from the table. And you could choose any entry you want. You could choose entry number 1 and use the numbers. You could choose entry number 2, You could choose entry number 3 to do it. Because it's a rate constant, they all should come out to be a constant number. That's the idea behind it. So you could choose any entry. You obviously can't mix and match, but you could choose any entry you like. So for our example here, I'm just going to choose the very first entry. And basically, I'm just going to put all those numbers into this now. And that would give me the rate, which was 1.2 times 10 to the minus 3 molar seconds, divided by our F2, which was 0.1 molar, divided by our ClO2, which was 0.01 molar. And if we do all that good stuff there, 1.2 exponent minus 3 divided by 0.1 divided by 0.01 gives us a 1.2 for our rate constant. What are the units I'm left with at this point? So molarity up on top, right? And one of the ones on the bottom cancel. So I'm left with 1 over molar seconds. Or obviously you could write it if you like, m minus 1, s minus 1, if you like to do it that way as well. Those units, as we might have talked about last time, are really the units that are very commonly seen for the rate constant of a second order reaction. So 1 over molar seconds or 1 over molar time is very common. Any questions on any of the parts of that calculation? So this is what we mean by finding the orders experimentally. And again, you will be provided obviously a table like this in a lot of problems. And may not always be 3 entries, could be 4, could be 5, could be a bunch of entries. But again, the goal when you're looking at that table is to find 2 entries where you keep one of the reactants constant and vary the other. In a rare case where maybe you have 3 reactants, you then would obviously want to find 2 entries where 2 of the reactants, right, remain constant and 1 varies. Again, most reactions that we deal with usually have how many reactants in a lot of cases? They usually or very commonly have like 1 reactant or 2, occasionally 3, but you really don't get reactions where there's a lot more than that sort of happening. And that's why, you know, we have things like only like 0 order, 1st order, 2nd order, because, you know, if you had like a 7th order reaction, you would need a lot of things are probably reacting in that reaction to do that. And that typically does not occur. Yeah. Any questions on that there? Okay. So, as we saw there with our rate laws, a couple important reminders as you go through it. Rate laws are always determined experimentally, so you'll always get tables. Will they always be really pretty numbers? They won't be, so that's why it's important to remember you could do the natural log of both sides to get you there, and you probably, for the most part, in a lot of cases, could round to the nearest whole number, although it doesn't necessarily have to be a whole number. It actually can be a decimal and stuff like that. In labs, you typically do sort of round to the nearest whole number and stuff like that. Reaction order is always determined in terms of reactants, so no products and rate laws. And again, the order of each reactant is not really the coefficient, although in some cases it may end up being the same number, but it's not really how you get it. All right, so if we have a rate equation with a rate law of the rates equal to K NO times O3, if the rate is 6.6 times 10 to the minus 5 molar seconds, when the concentration of NO is 1 times 10 to the minus 6, and O3 is 3 times 10 to the minus 6, what is the value of the rate constant? So take a moment or two, see what you come up with. Look at, so in this particular case, they did give us the rate law, which is K times NO times O3. Again, nothing is written here, which means it's assumed that it is 1st order with each of those, which means that overall, right, it would be in this case the same deal. 1 plus 1 would be 2nd order. Not that you need that for this question or anything like that. In this particular case, actually, we have the concentrations and we have the rate. So really, we're just going to rearrange and solve for K, which would be the rate divided by NO times O3. Popping in our numbers there gives us 6.6 times 10 to the minus 5 molar seconds divided by NO, which is 1 times 10 to the minus 6, and R3 times 10 to the minus 6. What do we get here? We get something. 6.6, we want to make sure we use our exponent, but to -5 divided by 1 to the negative 6 and divided by 3 to the negative 6. That's going to give us something in the ballpark of 2.20 times 10 to the 7. In this particular case, once again, the top molarity and one of the bottoms will cancel out, giving us what we just saw in the previous one, 1 over molar seconds as our units. First off, any question on the calculation there? So when we talk about, a large value for K, that's a pretty large value, and usually means that you will have a pretty good rate happening there in a lot of cases. And the reason for that is if you just look at a generic rate law, as we've been talking about, clearly if this number is a large number, right, just math wise, when you multiply against the other numbers, you will end up with a large number for the rate, right? So that's again the sort of the correlation between the rate constant and obviously the rate. And obviously if you have a smaller number there, when you multiply, you would get obviously a smaller sort of rate happening in that sort of situation. Obviously, concentration is dependent on that as well. But that's sort of the premise there behind, sort of a larger value to rate constant means it's happening a lot faster usually, and sort of a smaller value, obviously, it's happening smaller. Any questions on that there? All right, so once you do this one here, here's our experimental table. We want the complete rate law here. We want the value of the rate constant, and we want the overall order. So take a couple of minutes here, use this information, and calculate all those things there. You're gonna kind of see how you're doing here. So once again, we can start with sort of like the generic sort of rate law, which would be the rate's equal to K times S2O82 minus to the X and I minus here to the Y. Once again, only the reactants involved. We want to go to our table and again look for 2 entries where we're going to keep one of the reactants constant. So we can clearly see here up front, if we take 1 and 2, that will keep those 2 guys constant and it will vary the other. So that is what I'm going to start with here, experiments 1 and 2. Once again, we're going to choose in this case actually to put experiment 1 up on top. Again, you don't have to do that. But it will kind of give you, like I said, a little bit more whole numbers in a lot of cases. So that'll give us 2.2 times 10 to the minus 4 is equal to K times our 0.08 to the X and our 0.034 to the Y. Now I'm going to put everything from experiment 2 on the bottom, and that's going to give me 1.1 times 10 to the minus 4. K 0.08 to the X and 0.017 to the Y. Doing a little division here, that's going to give us a 2. Once again, our rate constant should be the same number top and bottom, so they should cancel. The X there for the order should be the same, so those guys will cancel. And obviously when we do this last one here, we get a 2 to the Y, which once again in this case means Y is equal to 1. So the order with respect to I minus is 1. Now that we did I minus, we now want to keep that one constant and vary the other one. And to do that, it looks like experiment 2 and experiment 3 will do that for us. So looking at experiment 2 and 3, in this case, I'm going to put experiments 3 information up on top since it has the larger rate. So 4.4 excuse me, times 10 to the minus 4 is equal to our 0.16 to the X, 0.17 to the Y. Now I'm going to put everything from 2 there, 1.1 times 10 to the minus 4, our K, excuse me, 0.08 to the X, and 0.17 to the Y. Doing our math here, that's going to give us a 4 in this case. The K's are going to cancel. When we do this division here, that will give us a 2 to the X. And once again, these guys here will completely cancel. In this case here, X would equal 2. So the order with respect to the S2O8 is going to be second order. That allows us to complete our rate law here. The rate would equal K times S2O82 minus to the second order. and I minus to the first order. First off, any questions on that part of the calculation? The overall order here would be, in this case, would be 2 plus 1, which would be a third order reaction. And again, that's found by just simply adding the orders together. At this point, once we have the orders, we can now go and rearrange our rate law here and solve for the K, and we can actually get the value of K. And once again, here we could take any one of these entries to do that. So I'm just going to rewrite it over here, the rate law. So the rate in this case was K S2O8 2 minus to the second, I minus here to the first. That means that the K would equal the rate divided by S2O8 2 minus squared and I minus. So if we take, we'll do the info from number 1, but again, you can do any one you like. That's going to give us 2.2 times 10 to the minus 4 molar seconds are 0.08 for this guy. And we do need to square it again because of the order there is 2. So we want to make sure that we do square it. And then our I minus is 0.034. So that is going to give us here 2.2 to the minus 4 divided by 0.08 squared divided by 0.034 in this case. Going to give us like a 1 point. I got there. 1.0. And the units here would be a molarity up on top, and the bottom will cancel. Leaves us 1 over molar squared seconds would be our unit, which again is different than what we saw for second order, and is also different what you see for first order. And as I mentioned before, the units there of the rate constant really do tell you what type of reaction you're dealing with. Any questions on any of that there? Yes, either one. Yeah. To solve for K, can you choose any of 3 entries? You should. So just to show you, unless I play with the numbers really badly here, if we pop in this stuff for number 2, for example, we would have 1.1 times 10 to the minus 4. I believe we have on that one there 0.08 and 0.07. So 0.08, 0.17, I think, right? 0.17, yep. 0.17. And again, if we do this here, 1.1 exponent minus 4 divided by our 0.08 squared and divided by 0.017 gets you the exact same number. So you could choose any entry you like. They all should give you the same result in terms of the rate constant, because it's a constant value over the whole reaction. So you could do any of the experiments you like. Yeah. Yep. Was that the same question, or yeah? Yeah, good. Okay. Other questions? Okay. So let's try another one here. Just make sure. Here we got 4 entries. So let's do the same thing. The complete rate law with the orders, the overall order of the reaction, and the value of the rate constant. So see what you come up with here. Okay, let's take a look, see how you're doing. So we got a few more entries in here. Maybe not as pretty perfect numbers that we get out of this sort of experimental one. But if we were starting kind of the same way, we'll do our rate is equal to K times our reactants, which are NO2, and our CO to the Y. That is a C, I think. There we go. And that's a U. So finish that off, make that head out. There we go. All right. So we actually have several different options when we look at keeping the CO constant, right? We could obviously keep it constant by doing those two. We could also, if we wanted to keep it constant by doing, say, this guy and this guy, We also could keep it constant by doing, say, this guy and this guy, right? So you have several different options as to which ones you could choose from the table. Again, in a real situation here, it really shouldn't matter which one you choose. So just to demonstrate that, we'll run through all the three options there and show you, how different they are, if they really are. So if we were to do, for example, 1 and 2, just to start it off with there, 1 and 2. And if we look at that, we will do our larger rate up on top, which in this case is 0.0082. So 0.0082 equals our K times our 0.2 to the X and our 0.1 to the Y. Putting our number 1 on the bottom there, 0.0021. Our K and our 0.1 to the X, 0.1 to the Y in this case. All right, so doing a little bit of math here, 0.0082 divided by 0.0021 gets you approximately, looks like, we'll call it 3.9048 equals this, and this should cancel. These guys here should essentially give you a 2 to the X, and these guys should completely cancel. Now, you could round that guy up to 4, right? But say you want to do the natural log of both sides, just again to show you how to do that. You would take the natural log of 3.9048. Personally, I'm going to take the entire number that's on my calculator. I'm then going to divide it by the natural log of 2, which is taking the natural log of this side and dividing it to the other side. That also then drops the X down to a regular X when you take the natural log of it and do that. When you do that, you take the natural log there of my entire number I had, divided by the natural log of 2, gets you essentially that X in this case. If we do a little bit of rounding, like 1.97 basically, which is approximately 2, right? Now, if I chose, was my other option there, 1 and 4 instead. Put in our numbers for 1 and 4. Once again, here we'll take the larger one on the bottom, on top, 0.033, which would be number 4. 0.4 to the X, 0.1 to the Y, and now putting number 1 again on the bottom there, 0.0021, RK, 0.1 to the X, and 0.1 to the Y. Once again, here, if we do a little division, 0.033 divided by 0.0021 gets us like a 15.7143. Again, take it to a few digits. We get these guys to cancel. This will now give us 4 to the X. These guys would cancel. Once again, I'm going to take the natural log of both sides and divide it over. Taking the natural log of the 15 point something number gets us like 2.75 divided by the natural log of 4 when you divide it over. Going to give us an X value in this case of 1.99 basically on some rounding, which once again is pretty close to 2 in this case. Lastly, if you chose to do number 2 and number 4 for that, we'll put in this case number 4 back up on top. And our 0.1 to the Y. We'll put number 2 there on the bottom, 0.0082, K, 0.2, 0.10. Once again, here we'll take 0.033 divided by 0.0082, 4.0244, we'll call it. These guys will cancel. That's going to give us a 2 to the X. Once again, these will completely cancel. Doing the natural log of both sides there gets us actually like an X value of 2.01, which again is approximately 2. So you can see here, by the way, you don't have to do all 3 of them, right? But you can see here, no matter sort of which combination that you choose, really from that table in this particular example, you should end up with pretty much 2 as the order for the NO2 in this case. And again, you may not get perfectly pretty numbers, so you can do the natural log. And I would say in most cases, it's probably safe to round to kind of the nearest whole number in most situations that you come across. Any questions first off on any of that there? So once again, you don't have to do all three of them. You can just choose any of the three. And now that we did all three of them, we will then go back and thank goodness there's only one choice here to keep this guy constant. And that looks like number 2 and number 3 will keep our NO2 constant while varying our other. So I'll do that on the next page here. So 0.0083, I think. So 2 and 3 is, I think, what we're shooting for there. And we're going to do number 3 up on top. So that's 0.0083. It's equal to our K 0.2 and 0.2. That's easy. 0.2 to the X, 0.2 to the Y. And our number 2 is 0.0082. And that was 0.1, 0.2 and 0.1. Okay. So here, essentially, you could call it a 1, but it's really 1 point something, like 1.0 something. This will give us some K's that cancel. These guys will completely cancel. When these guys cancel, as that's not a 16, that's a 10. We will do a 2 to the Y. In this case, Y would equal 0, right? Anything that is 0 order would equal 1, basically, right? You could also get that by taking the natural log of 1, which should give you 0, divided by the natural log of 2, which should still give you 0. So in this case, the order with respect to, what was that there? CO is 0 order. So the completed rate law in this case would be the rate is equal to K times the concentration of NO2. And that was to the second order, I believe. And our CO to the 0 order, which in most cases means you really don't necessarily need to even put it into the rate law. You could reduce it down to just the rate is equal to K times NO2 squared. If you want to put it in, you for sure need to put the 0, because if you do not put the 0 and just leave it blank, it implies what? That it's first order, right? So again, if you do include it, which is perfectly fine to do, you got to make sure you put the 0 on that particular one. Otherwise, again, I would indicate something different. The overall order here would then be, it would be second order, right? 2 plus 0 is second order in this case. And now that we do have the completed rate law, we could again solve for K, which in this case would be the rate is divided by NO2 squared. And once again, as we talked about, you could grab any entry off that table. So I'll just roll with, why not? We'll do the second one for it to mix it up a little bit. We'll do 0.0082. 0.0082 molar seconds divided by our N2 for that, which is 0.2. And once again, we've got to make sure that we do square it. So that would be 0.0082 divided by 0.2 squared. Going to give us, looks like 0.21, if I did that math right, I think. Right. And units here is going to be 1 over molar seconds. Yeah. And again, that's what we typically do see with a second order reaction. Any questions on any parts of that calculation there? Yes. Did you say NO2 would have more impact on the rate of the reaction? Is that what you asked? Yeah, it would, obviously, right? So this would be a situation here, obviously, if we change the concentration of CO and doubled it, for example, right? It really won't have any effect, right? So we actually have the numbers here. So if we have the complete rate law, which would be 0.21, right? So the rate here would equal 0.21 times our NO. And let's just say, for example, we had 2 molar for our NO, right? And we had 2 molar for our CO to start with, right? And we did this. the rate that we would roll in with this reaction based on those concentrations would be 2 squared times 0.21. And we would end up with a rate of 0.84. The rate here would be molarity, and molarity will cancel molarity over seconds, right? Now to your question is, this is the CO. So if we doubled the CO in this reaction, right, we would end up with the rate is equal to 0.21 molar seconds, still leaving the first guy at 2 molar, and we doubled this guy to 4 molar. Once again, this is going to be 1, right? Which means we will end up with the exact same rate, right? It's not going to change it at all. So you would definitely, in this particular example, have to change the NO2 if you either want to just kind of speed it up or slow it down in this case. Yeah. Yes. Yeah, I would say you should probably round to the nearest whole number in most cases. Again, especially in experimental cases, a lot of book problems will come out pretty kind of nice numbers, if you will. But you should definitely probably, in most experimental cases, round up, and even probably in book cases, it's probably pretty safe to round, unless it's really, really far away. Yeah. So like in a lot of those examples we just did, right? So we had something like, I don't know, 1.96, which is pretty close to 2. So I would say in most cases, you should be pretty safe to round. Yeah, so again, in that case, 0.01 would technically kind of round to the nearest whole number of 0, right? Yeah. Is it impossible to have an order that's maybe like a decimal or a fraction? It's not, actually. But I would say in probably most cases, fairly safe to get yourself to a whole number if you're pretty close to it. Other questions? All right, let's try maybe one more here to wrap it up. I would think. All right, so what I was gonna say was, I think we're gonna lay it up here since we're getting towards the end here. We will do this example at the very beginning next time and continue lecturing.